Hello, we're team 23046, and our project was to develop, build, and demonstrate a sensor system that can be mounted to an autonomous tractor to recognize the type of implements that the tractor is pulling, the implement's position, and the hitch angle relative of the implement to the tractor. Our project serves as a proof of design of this concept using trucks and U-Haul trailers. Our project is sponsored by AGCO Corporations and JCA Technologies, and our mentor is Jim Sweetman. My name is Gavin Caldwell. I'm a computer engineer, and I'm the team lead on this project.
Hi, I'm Case Passon. I'm an optical engineer and the procurement lead on this project.
Hi, I'm Howard Yowit. I'm a senior electrical engineer.
Hey guys, my name is Everett Schaefer, and I'm an optical engineer on the team.
Hi, my name's Jessica Grove, and I'm the industrial engineer on the project.
I'm Brett Miller, and I'm the biosystems engineer on the team.
The Vabaya system is a big step forward for agricultural automation technology. Most high-end tractors already have automation technology integrated within them, but the implements that a tractor can pull, baler, a seeder, a forage wagon, these things do not. And you cannot simply add a big piece of equipment to an automation system and expect it to run well. So rather than trying to automate every implement you may own, the Vabaya system aims to centralize the automation technology on the tractor itself, and it allowed to be the capability to handle different implements being attached. This will increase overall efficiency and productivity in an agricultural setting.
To start off with our system requirements, they're broken down into 4 categories: our performance requirements, our output requirements, our environmental requirements, and our customer constraints. We'd like to highlight our 4 major system requirements, which include our visual accuracy, pose accuracy, degree accuracy, and voltage.
To integrate all of our hardware components together and process data, we're using a computing framework, a programming framework called ROS, specifically ROS2 Foxy. ROS allows robotics applications to connect all of our components together through nodes and topics. This is how we pass data to one another while our system is running. We have some packages for ROS built in C++ for our LiDAR, and other packages built in Python for our OAK-D camera. Depth AI is the Python package that is used to interact with the camera and gives the OAK-D and gives API to activate its different functions. We use this Python package to initialize the RGB color camera of the OAK, as well as load on our custom neural network model. To process our LiDAR data, we use a software library called PCL, or Point Cloud Library. This software library gives us a lot of neat tools to be able to process the 3D points, the most important one being a plane segmentation. So it segments all the points parallel to the plane of the implement and returns that plane equation. Once we have that plane equation, we use the normal vector from that plane and calculate its angle from the hitch just using a simple geometric linear algebra calculation. We also use this normal vector for our pose estimation. There are 2 parts for a pose message in ROS: the position, which we are pulling straight from the LiDAR coordinates, which are already in XYZ format, and the orientation. We use the normal vector compared to our axis vector coming out of the sensor to calculate what's called a quaternion through this equation. A quaternion is just a mathematical object that is a convenient way to represent roll, pitch, and yaw angles.
For our object recognition algorithm, we utilize a platform called RoboFlow. RoboFlow is a universal conversion tool for machine learning models. We took images of 2 different types of trailers and uploaded them and annotated them within RoboFlow. We then pre-trained a model utilizing the YOLO v5 framework on RoboFlow to be then uploaded further onto the OAK. For that, we had to download or export our pre-trained model from the RoboFlow. Then we utilized the Ultralytics pipeline to convert the YOLO v5 model to an ONNX file to then be converted and uploaded to the OAK device utilizing Depth AI packages. For our system's electrical configuration, we used 12 volts from the vehicle's battery and supplied it to the distribution block. And from the distribution block, the 12 volts is stepped down from 12 volts to 5 volts and fed into our network switch, as well as the Jetson Nano. 12 volts is also taken from the distribution block and supplied into the Livix Mid-40, as well as the Oak D PoE injector, which steps the 12 volts up from 12 volts to 48 volts and supplies the Oak D PoE with power.
The Vabaya needs to be capable of sensing in multiple different environments, and as such we did a Q analysis on different types of sensors with different sensing methods to find the best method in order to deal with high light environments, low light environments, and adverse environments with sand or rain. And we decided on the Oak D PoE, which is a 3D stereo sensor, and the Livix Mid-40, a LiDAR sensor, which we believe in combination should be able to complete everything no matter what environment it is in. We also decided to use a Jetson Nano as our microcontroller. We originally planned on using a Raspberry Pi, but switched to the Jetson as we believed we needed more computing capabilities for this project.
Getting into the hardware portion of our project, we were tasked with designing a 3D enclosure that would house our sensors, computer, and vision components for the Vabaya system. We developed an initial SolidWorks model with plans to 3D print the parts of the enclosure for rapid development. Unfortunately, we encountered various problems with the 3D printers and were forced to prototype the system using wood wall sides around the first 3D part that was properly printed in order to meet ISR deadlines. This initial test fit showed us where we needed to modify our design in order to better integrate each component properly. Once we had sourced properly working 3D printers, in the downtime, we investigated the metal fabrication route, but found that this would not work to suit our needs. Once we properly printed all of the components, we were then able to integrate our system and found that the changes we had made were able to suit our components properly and integrating them better to suit their needs.
The overall 3D design of this project is made up of a magnet that sits at the top of a truck, and then a bracket made at a 10-degree angle to look down at the implement, and then the 3D housing that we made earlier. And the reason we did it in this way is with the magnets to create more of a modularity to it, where we could take it, mount it onto different trucks or in the future tractors.
After conducting thorough testing with varying obscurations, the Vabaya system was able to accurately identify our implements within our 80% confidence interval. It's important to note that there were instances where our system was detecting an implement when no implement was present. However, our system was able to accurately identify our implements when they were present and were never confusing the two implements we were testing with. The Vabaya system was able to accurately compute the distance between our sensor and the front face of the implement within our 15 centimeter margin. Our system was also able to compute the hitch angle within our 10-degree margin. And lastly, we were successfully able to power all components of our Vabaya system off of 12 volt to DC from the vehicle battery.
In conclusion, our system was able to meet the key system requirements laid out by our team and sponsor. We received no inherited components or had any experience prior to this project, and now we have a fully functioning robotic system. There's certainly room for improvement, such as increasing the durability of the environmental housing. However, we were able to demonstrate that this system has the capability to achieve the vision laid out by our sponsor. Once again, we're Team 23046, and thanks for watching.